Hello everyone. Today in this lecture I will discuss about the shear force and bending moment diagram of a simply supported beam. So now I will start the different cases. The first I will discuss about the point load, second about the UDL, and third one about the UVL. So very first case I am taking, that is simply supported beam, simply supported beam having point load at midpoint. Simply supported beam having point load at midpoint. This is a simply supported beam. Simply supported beam. It has a point load W at mid span. The length of this beam is L. Length of this beam is L. Length of this beam is L. Now this is A point, this one is a B. Very first of all, we have to find out the reaction at point A and B. Now applying the formula sigma Fx equal to 0. Sigma Fx, here in this beam there is a no load in horizontal direction, so Fx equal to 0. Leave it. And sigma, next formula, that is sigma Fy equal to 0. It means algebraic sum of all the forces acting vertically equal to 0. Here the vertical force, that is reaction Ra. Here is the reaction Rb. Ra plus Rb. Ra plus Rb equal to W. Upward force equal to downward force. This is equation number first. For solving two unknown, we have two equations. So for next equation we have to apply the moment about point A. So taking moment about point A, taking moment about point A, Rb into L. This movement is anti-clockwise, and the moment due to this load is clockwise. So anti-clockwise movement equal to clockwise movement. So Rb into L equal to W into L by 2. As load is acting at mid of this span, so L cancel. Rb equal to W by 2. Similarly, by putting this Rb in equation number 1, we can calculate the value of Ra. That is Ra equal to W minus W by 2. That is W by 2. Hence, the value of Ra equal to W by 2 and the Rb equal to W by 2. This is Ra equal to W by 2. This Rb equal to W by 2. This Rb equal to W by 2. Now I have this point is Let's suppose this is a C point at which the point whose load is acting. Now we have take a section XX in the portion of BC. So consider portion BC portion. For shear stress Fx in portion BC, Fx equal to the right side of this section. There is only one force, that is RB, W by 2. It is acting upward. So upward force, in the sign convention, the upward force is positive at the right section. So plus W by 2. This is a constant value. It means the shear force in between C and B will remain same. At point B, Fb equal to W by 2. At point C, when x equal to L by 2, Fc right equal to W by 2. As we don't have considered the value W that is acting at point C. So I have to consider only the right portion of the C, just the right portion. So just right portion, the FCR equal to W by 2. In this way I have calculated shear force at point B and at point C, right to the C. Now I have to consider the section in between A and C for the shear force, and this distance is x, and this is also x variable. I have to extend this value from here to here, that is x. So for portion AC, shear force Fx equal to algebraic sum of all the forces that are acting right side of the section. It means RB, the load is acting upward, it is taken positive, that is W by 2, and next load is W, that is acting downward, minus W, because of this load is acting downward forces, shear forces are negative. So this value is W by 2. Fx equal to minus W by 2. This is a constant value. So in between A and C, the variation of shear force is constant. So this is a constant. It means FC equal to minus K W by 2, and FA equal to minus K W by 2. If we consider at A, then FA equal to minus W by 2 plus K W by 2 equal to 0. So now I have to draw the shear force diagram of this beam. Extend this line to lower end. Draw horizontal line. This is A point, this is C point, this one is B point. At B point, the shear force, value of shear force is W by 2. Take a appropriate distance, W by 2. This is a constant value. Here the value of shear force at point C is minus K W by 2. W by 2. Here is W by 2 only. Again, in between A and C, the shear force is constant, and the value of shear force is minus W by 2, and at point A it is 0. This is a negative shear force, this is a positive shear force. This is negative and this one is positive. In this way, we can draw the shear force diagram of simply supported beam. Now I will go for a bending moment diagram of this simply supported beam. For section BC, BC section, for this section, mx equal to, from here you have to take the bending moment, and the tendency of this moment is to rotate the beam in anti-clockwise direction. So anti-clockwise direction, it means it is making a sagging. Beam is sagging type, so it is a positive bending moment is plus W by 2 into x, that is Wx by 2. This is a linear variation. This is a linear variation. Means bending moment vary in between C and B linearly. It depends on the x only. Bending moment at point B, bending moment at point B, that is x equal to 0 and B equal to W by 2 into 0, that is 0. And so bending moment at a fixed end, at the support, bending moment at the support is 0 in case of simply supported beam. Now I have to calculate bending moment at point C, that is a midpoint. For midpoint, bending moment at point C, x equal to L by 2, m C equal to W by 2. Put the value here, x W by 2 into L by 2, that is WL by 4. And the bending moment at point C is WL by 4. This is the maximum value of bending moment in between the beam A and B. Similarly, we can calculate the value of bending moment at point A. At point A, the bending moment will be 0 at point A. We can calculate also the bending moment at point A. There is a similarity in between CB and AC. So there will be a reflection of BC in AC. If bending moment at point B is 0, then also the bending moment will be 0 at point A. We can also calculate it also. So MA equal to W by 2 into L minus W into L by 2, that is equal to 0. Now I have to draw the shear force bending moment diagram. Just draw the line A, C and B. The bending moment at point B equal to 0 and bending moment at point C is equal to WL by 4, and this bending moment is positive in nature. So here is 0 and this one is, here is WL by 4. Here is also 0, but it very linear. As this value is positive, this is a bending moment diagram of simply supported beam. This is a shear force diagram. First one was. So in this way, we can calculate the shear force and bending moment diagram of simply supported beam having a point load at the midpoint, and this load can be applied anywhere in between the A and B. For that, we can calculate the shear force and bending moment diagram, and similarly, the shear force and bending moment diagram can be plotted over here, and we can find out whether shear force, where is the shear force maximum and where the bending moment is maximum. This bending moment can be utilized in the theory of bending, where the maximum bending moment is considered. At that time, we can utilize these values, shear force bending moment diagram. From shear force bending moment diagram, we can utilize this value for designing the beam. WL by 4, this is the maximum value of bending moment diagram for simply supported beam having point load at the midpoint. Now I will take another case for the UDL in simply supported beam. So, any beam can have a point load, uniformly distributed load, or U bearing load. So for that, I have to calculate all the cases, the bending moment and shear force, the value of shear force and bending moment. So that I will take another case, second case, the simply supported beam having UDL, uniformly distributed load. This is a symbol of uniformly distributed load. So I have applied this UDL load to core of the beam. The intensity of the load of this beam is W per unit length. Length of this beam is L. Length of this beam is L. Length of this beam is L. Reaction at point A is RA, and the reaction at point B is RB. So first, in simply supported beam, we have to calculate the value of RA and RB in the starting. After that, we have to proceed to find out the shear force and bending moment diagram of a given problem. So first of all, I have to calculate the value of RA and RB, and we can see that there is a similarity in the beam. So we can easily calculate the value of RA and RB. So this load can be divided equally. That is RA equal to RB. You can also calculate by taking equilibrium equations. RA equal to RB, that is W into L. W is the weight per unit length. A total length of this beam is L, so that the total weight of this beam is WL. So RA plus RB equal to WL by 2. It is equally divided. So in this way, we can easily calculate the value of support reaction RA and RB. So this is WL by 2, and here is also WL by 2. Now I have to start to find out the shear force. For that, I have to take a section in between A and B at a distance x from support B. For shear force calculation, shear force Fx, that is shear force in between this section and B, that is algebraic sum of all forces that are acting right side, right portion of this beam, that is Fx equal to, first load is this reaction RB, this is a WL by 2, and acting upward forces we are taking positive, this is positive WL by 2. Another force that are acting in this beam is UDL load. UDL length of this UDL is x. The total load of this portion is W into x. W into x. The direction of this load is downward. So downward load we have taken negative by sign convention. This is equation number 6. We can see that this force, shear force, vary linearly because it depends on the x. By using this equation, we can find out shear force at different points of this beam. Now first we have to find out the shear force at point B, that is x equal to 0. Putting x equal to 0, we can find out the value of shear force at point B. FB equal to WL by 2 minus W into 0, that is WL by 2. At point A, when x equal to L, put the x equal to L in the first equation, we can find out the value of the shear force, that is FA equal to WL by 2 minus W into x. This is equal to minus KWL by 2. This is a negative. So by using these values, we can draw the shear force diagram and bend shear force diagram. This is a horizontal line A and this one is B. Here shear force at point B is WL by 2, this is a positive, and here is at point A, this is a negative, this is a WL by 2, this is WL by 2. This is a negative, this is a positive. Shear force from midpoint to the B is positive, and from midpoint to support A is negative. Here at midpoint, the value of shear force is 0. At midpoint, the shear force is 0. You have to remember this figure, and we can utilize these values when we are calculating when we are designing the beam. At that point, we have to calculate the shear force at different point by utilizing this figure. So now I have to calculate the value of bending moment at different sections. For that, I have to first derive an equation for bending moment diagram. Again, consider same section x6 at a distance x from the support B. For that, the bending moment for bending moment for bending moment. mx equal to what is mx? The bending moment at section x. Bending moment at section x. Now we have to take the first force, bending moment due to this force, that is RB, reaction. It is acting upward direction and it rotates anti-clockwise. The shape of this beam will be sagging. A sagging moment is taken as a positive moment. So plus W by 2 into small w, L by 2 into x. This is a movement due to this way. And now I have to find out the movement due to the UDL. UDL, the total weight of this UDL is W into x. W into x, the total weight, and the CG of this load will be midpoint between x and b. So this distance will be x by 2. The bending moment due to the UDL load, that is UDL load is Wx, W into x, into distance between this load, centroid, and the x-axis section is x by 2, x by 2. That is W Lx by 2 minus Wx square by 2. This is equation number 2. By utilizing this equation, we can find out the bending moment at different portion of this beam. First, I have to take bending moment at point B, that is x equal to 0. While we put x equal to 0 in this equation, the bending moment will be 0, mb equal to 0. At support, the value of bending moment is 0. And at point A, bending moment at point A means x equal to L. For the x equal to L in this equation, you will find out the value of M A equal to WL into L by 2 minus WL square by 2, that is 0. Again, we can see that bending moment at both support at point A and at point B is 0. So what will happen in between A and B? We have to find out the value of bending moment in between A and B. For that case, we know that the value of bending moment will be maximum where the value of shear force is 0. It means shear force is 0 over here. At this point, the bending moment will be maximum. So this is a midpoint. We can easily find out because there is a similarity in between this figure and this figure. So easily we can find out that the x equal to L by 2. At x equal to L by 2, the value of bending moment is maximum, because here shear force, value of shear force is 0. Shear force equal to 0. Here shear force is 0. If shear force is 0, it means the bending moment will be maximum. Bending moment will be maximum. So now to put the value of x equal to 2. In the equation number 2, to find out the maximum value of bending moment, you can easily find out at x equal to L by 2, that is at point 2, we can say C is WL by 2 into L by 2 minus WL by 2 square divided by 2. It means WL square by 4 minus WL square by 8. That is WL square by 4. At this point, the value of bending moment is maximum. It means suppose this is a point where WL square by 4. WL square by WL square by 8 out of 4. This is the 8. WL square by 8. Variation of bending moment in between A and B is parabola. Variation of bending moment in between A and B is parabolic. We can easily say from this figure, these equations, because it depends on the x square. So this is a formula of y equal to ax square. Okay. So now I have to draw bending moment diagram. This is a positive bending moment diagram. This is positive bending moment diagram. So in this way we can calculate the value of a bending moment diagram, maximum bending moment diagram, that are acting in between the A and B, in beam. Suppose this is a beam. This beam can be used in your houses, buildings, where the load is maximum, bending moment is maximum, can be calculated by using this. According to that, we can design the buildings. This result, that is maximum bending moment, can be utilized in the theory of pure bending. Okay, students, this can be utilized because the formula of pure bending is m upon I equal to f upon y equal to sigma E by r. In this case, when you are going to find out the value of the shear force, you have to utilize this relation, that is F equal to m over I into y. So this is a case. At the time of designing, we have to find out the maximum shear force that is acting, maximum bending moment or maximum shear stress that is acting on your beam. So for that, we have to utilize this value of maximum bending moment in this figure. So this is a very most important result that are coming out from the bending moment and shear force diagram. Okay, students, thank you very much.